Chapter 3, Section 6, Elasticity of Demand. Given a demand function, d of x, which will be a function of x, where x is the price, the elasticity of demand is negative x times d prime of x all over d of x. We say that when the elasticity of demand is less than 1, demand is inelastic. More about this word in a bit. When the elasticity of demand is 1 exactly, demand has unit elasticity. And when elasticity of demand is greater than 1, demand is elastic. One more thing about this one in the middle, footnote, when the elasticity of demand is 1 exactly, that is when revenue is at a maximum. Make sure you have all this written down. And then on page 376, exercise 8, the demand function is given. The square root of 300 minus x. And the directions there are for 3 parts. Part A is to find the elasticity. Part B, find the elasticity at the given price. And also state whether demand is elastic or inelastic. And part C is to find the values of x for which the total revenue is at a maximum, where x is in dollars. Since d of x is equal to, in parentheses, 300 minus x raised to the 1/2 exponent, d prime of x is the 1/2 exponent times the number in front, understood to be a 1, 1/2 times 1. Copy what's in the parentheses. Subtract 1 from this exponent. 1/2 minus 1 is negative 1/2. And we multiply by the derivative of what is inside the parentheses. The derivative of 300 minus 1x is negative 1. So d prime of x is negative 1 over 2 radical 300 minus x. The negative that's over here is right here. The 1/2 is there, 1/2, and we make the exponent positive by putting 300 minus x to the 1/2 in the denominator. So for part A, S for the elasticity, which is a function of x, the definition of elasticity is negative x times d prime of x all over d of x. So for this exercise, the elasticity is negative x times what we just got there, negative 1 over 2 radical 300 minus x, over d of x. D of x is the function that was given, radical 300 minus x. In a simpler form, this is a negative times a negative, so we're going to write positive x, that's x times 1, over 2 radical 300 minus x. And this division symbol right here, this red division, can be rewritten as multiplication by the reciprocal. The reciprocal of radical 300 minus x is 1 over radical 300 minus x. Dividing by something is the same as multiplying by the reciprocal. The elasticity is x times 1 over 2. When we have a radical times the exact same radical, we end up with just what is inside the radical. The radical disappears. Radical 300 minus x times radical 300 minus x is just 300 minus x. This is the elasticity function. For part B, it says find the elasticity at the given price. The given price in the exercise is 250. X is the price. We're going to replace every x with 250. The eccentricity at the given price is 250 over 2 times 300 minus 250, which comes out to be 2.5. That is the elasticity at the given price. Since that number is greater than 1, we say demand is elastic. Which means when demand is elastic, we mean an increase in price will bring a decrease in revenue. Demand is elastic means an increase in price brings a decrease in revenue. And demand is elastic whenever the elasticity is greater than 1. If the demand were inelastic, that would mean an increase in price would bring an increase in the revenue. So part C, we are to find the values of x for which the total revenue is maximum. Revenue is maximum when the elasticity function is equal to 1 exactly. The elasticity function that we found up above in that box, x over 2 times 300 minus x. We need to know when that is equal to 1. To solve this equation, we cross multiply. X times 1 equals 2 times 300 minus x. When two fractions are equal, the cross products are equal. X equals 600 minus 2x, distributing the 2. Add 2x to both sides, and divide both sides by 3. So when x, which represents the price, is $200, that's when the revenue will be maximum. The next section, Chapter 4, Section 1, is called anti-differentiation. Which means when we're given a function, we want to know what it is the derivative of. Given something, we're going to find what it is the derivative of. So it's the opposite of finding the derivative. And here are some rules to learn. Here's the first few rules for anti-differentiation. The antiderivative of dx is x. So notice the symbol that I just wrote. It's a stretched out letter S. When we write that, we say the antiderivative of whatever follows. What's in between this symbol and the dx is called the integrand. So in this, there's understood a 1 there. You can't see it over here, but it's understood. In this rule, 1 is called the integrand. It's what we're finding the antiderivative of. And well, I'll write a couple more rules and then we'll do some examples. The second rule is the antiderivative of x raised to a number, dx, is x raised to that number, the exponent, plus 1, over the same thing, plus any constant. By the way, plus c is part of that rule also. C stands for any constant. After we write the rules, the examples will make this more clear. This second rule only applies if the number, which is the exponent, is not -1. There's 2 more rules for this video. The integral of 1 over x dx is the natural log of x plus any constant, and that x has to be greater than 0. In that third rule. And the last rule for today is the integral of e, the number e, raised to the ax dx is equal to 1 over a times e to the ax plus any constant, where the a is a number, but it would be any number other than 0. So sometimes when I write this symbol, I say antiderivative. And sometimes I'll say the word integral. So you might get confused, but I use these words interchangeably. And what's in between this symbol and somewhere over to the right, there's always going to be a dx. What's inside here, as I said earlier, is what we call the integrand. It'll be between the integral symbol and the dx. And I think the best thing is to just do a few examples that are on page 397. Exercise 44. It says find the integral, or I could say antiderivative, of 2e to the 6x minus 3 over x plus the cube root of x to the fourth. So the goal here is to find something whose derivative is what's inside this green thing. So it's important to repeat the goal. The goal, I'm just going to say the words, I won't write them down. We're going to find a function whose derivative is what I put a green box around. The symbol here with the dx at the end is just the symbol we use, which means find some function whose derivative is what I put a green box around, whose derivative is the integrand. So first thing is there's three terms. The integrand has three terms, so we can distribute and write three separate integrals. We can write the integral of the first term, and we also distribute the dx, minus the integral of the second term, dx, plus the integral of the third term. So it's like three separate problems right here. When we do each of these, we actually, in the next step, we're actually going to ignore the integral symbol and the dx. Well, actually, it's too soon to say that. Well, I'll take that back for now. For each term here, if there's a constant that's multiplied, like the 2, we can move it. We move constants that are multiplied to the left of the integral symbol. The same thing with this 3. We're going to take this 3 and put it to the left of the integral symbol. And this third one, instead of writing the cube root of x to the fourth, we're going to write x to the 4/3. So now this thing in the blue, the 2 in front we just bring down. And if you look at the rules that we just wrote, the integral of e to the 6x, applying the rule, the fourth rule that was listed, it's 1 over this number here times e to the 6x. In the rule it says times e to the ax. In this case it means e to the 6x. The dx just disappears the same way the stretched out s disappeared. Copy the minus, copy the 3. So we're going to do this term in red. Copy the minus and copy the 3. This middle one is the third rule in the list of rules you had. The integral of 1 over x dx is the natural log of x. We'll use purple for this one. The plus comes down. This is an application of the second rule. The integral of x to a number dx is x to this number plus 1. 4/3 plus 3/3 is 7/3 over the same number, 7/3. And so each of these problems here, the blue one, the red one, and the purple one, each one really has a plus c attached to it. All we do is put 1 plus c at the end of the entire thing. And now I'll explain why this is correct. Well, first, we'll simplify. 2 times 1/6 is 2/6, which is a third. So we have a third e to the 6x minus 3 times the natural log of x plus, and this last purple We have divided by 7/3. Dividing by 7/3 is the same as multiplying by the reciprocal 3/7. And now we're going to do a little proof that that is correct. So I'm going to write ANS for answer. We just got this answer. 1/3 e to the 6x minus 3 natural log x plus 3/7 x to the 7/3 plus c, c meaning any constant. The derivative of that answer, answer prime, we bring down the 1/3, and if we remember the derivative rules, the derivative of e to the 6x is itself e to the 6x times the derivative of this exponent by the chain rule. Copy the minus, copy the 3. The derivative of the natural log of something is 1 over the something. And for the third term here, the derivative of a number times x to a number, we multiply the exponent and the number in front. We multiply 7/3 times 3/7, and we get 21 over 21. The x we copy, and the 7/3, when we take the derivative, we subtract 1. That 7/3 minus 1 is 4/3. And c means any constant. The derivative of any constant is 0. Notice here we have 1/6 times 6. 1/6 times 6. Okay, that's a mistake because I'm making a mistake in the check because that 1/3 should get brought down. I don't know how it turned into a 6. So when finding the derivative, the 1/3 we just bring down. The derivative of e to the 6x is e to the 6x times 6. So now, see how we have 1/3 times 6? 1/3 times 6 is 2. Bring down that e to the 6x. Then we have minus 3 times 1 over x. It is 3 over x. And then we have plus 21 over 21. That's 1. X to the 4/3 can be written as the cube root of x to the 4th. And then add nothing to that. Please notice this is exactly the original integrand up here in the screen box. So we call this the check. We found the function right here in the black box whose derivative is what's in the green box. Over here to the right, that's the check. So we'll do one more example in this video. It's number 62. The company determines that the marginal cost, symbolize C prime, marginal cost of producing the xth unit of a product is x to the 3rd minus x. And the question is to find the total cost function. So instead of being given the cost function and having to find the marginal cost, this is backwards. We have the marginal cost given, and we have to find the cost function. And we are going to assume that the fixed costs are $6,500. Since C prime is given and we want C of x, C of x has to be the antiderivative of C prime. So when we put this blue symbol, we always include it with this blue symbol, and that indicates that we want the antiderivative of what's in between the blue. And here's how we do it. We distribute this both blue symbols, like so. write the antiderivative of the first term with a dx minus the antiderivative of the second term with a dx. And both of these terms use, I'll go back and show you which formula. They're both going to use this formula. The integral of x to a number dx is x to the number plus 1 over the number plus 1. As long as that number right there is not negative 1. So we're going to use that formula twice, where we are over here. Bring down c of x equals the antiderivative of x to this number is x to this number plus 1 over the same thing I just wrote. Copy the minus. The integral or antiderivative of x to this number dx is x to that number plus 1 over the same thing I just wrote. Now in the formula we say plus any constant. In this case we're going to say the constant is $6,500. So we'll take a minute to talk about why this is the right answer. C of x equals, there's a 1 here, so let's write 1/4 times x to the 4th minus, there's a 1 there, so we can write 1/2 times x to the 2nd plus 6,500. Let's think about why this is correct. So that is correct because if c of x is this, c prime of x, the derivative of 1/4 x to the 4th is 1x to the 3rd. The derivative of negative 1/2 x squared is negative 1x to the 1st. And the derivative of 6,500 is 0. So that's a check because this was given. Also, using our answer up here, the cost of producing 0 units using the answer we got up here would be 1/4 times 0 to the 4th minus 1/2 times 0 squared plus 6,500. In other words, the cost of producing 0 units is 6,500, which makes sense, which is what it's supposed to be. The fixed costs are $6,500. So all of the given information checks with this answer. That's why that is the correct answer.